Very good morning, guys. Can you hear me?
Yes, we can.
So before we get started, I just want to see if there are any questions or comments about either last week's lecture or the homework or in general. Okay, if that's not the case, then let's get started. So I want to start out by recapping a few of the things we talked about last time. So what we were talking about last time was a simulation. Right? So we're talking about Monte Carlo simulation. And right, so the starting point is that this is uniform on the interval 0, 1. So that means that the probability that the random variable is less than a constant little u, this is just equal to u for any u between 0 and 1, right? That's what it means to be uniform. And so what we did was to get a general, or maybe we should, so the estimate we would get is that if you take a function, I think we call it g, right? So that's going to be from, well, let's say from 0, 1 to 0 into r. We will be interested in computing an expectation of the form g of u. We would approximate this by saying, well, we look at 1 over n, and then we will be summing g of little u of n, where u of n, they are, well, the numbers between 0 and 1, they are samples of the random variable u. And one thing we were talking about, so last time we were talking about we discussed these antithetic variables. Let me see if I can spell it right. Antithetic. Just look up the right spelling of it. We discussed antithetic variables. So this is this trick to reduce variance. And what was we observed? Well, if u is uniform on that interval 0 to 1, and that's going to imply that 1 minus u is also uniform. Right, so what we could do is, well, we could note then that the expectation of g of u, well, this is obviously going to be the same as 1/2, and then the expectation of g of u plus g of 1 minus u, right? Because you have the same distribution. So both these expectations, the expectation of g of u and the expectation of g of 1 minus u, it'll be the same, and it'll be both equal to this. So we add them up, take the average. And so we could sample. instead of the formula here. So we could alternatively use that this expectation could be approximated by, well, what would it be? 1 over n, the sum, and then you had 1/2 g of un plus g of 1 minus un. And the benefit would be that the variance of 1/2 g of u plus g of 1 minus u, this should be smaller, hopefully a lot smaller than the variance of g of u. So you get a more accurate procedure of doing this. And there was a question. There was a student that asked, so when does this work? I don't know if that student who asked the question is here again today, but one of you last time asked about when does this actually work? And the debate was, we need to look at the covariance. Is there going to be a question about covariance? So I was playing around with this a little bit, and so that's what I want to start by showing you. The result is, we call it a theorem. The theorem is that if G is monotone, so this is either increasing or decreasing. For us, the G is going to be a payout, and it'll typically be increasing, but the result works for both increasing and decreasing. If G is monotone, then this covariance that we were interested in from last time, G of u with G of 1 minus u, that covariance is going to be negative. And that's what we want. All right, so the proof, there are 2 steps. It's not that difficult. There are 2 steps to it. So the first step is, so step 1. Let f and g be increasing functions. So take 2 functions and they are increasing. So what does it mean for functions to be increasing? So what it means is that if I take x bigger than y, then I'll have that f of x minus f of y. That's going to be positive. Right, so if I multiply it onto the same thing with g of x minus g of y, so now this is going to be positive. Right, so we're going to get this. And if I do the opposite, if I take x less than y, so the first one is that case. If I have x less than y, well, then the inequalities are going to flip. I'm going to get that f of x is less than f of y, I'm going to get that g of x is less than g of y. But when I multiply them together, I'm going to get that f of x minus f of y, right? So now that's going to be negative. So this is negative. And I multiplied on to g of x minus g of y. This is also going to be negative. So I take two negative numbers, multiply them, and get something that's positive. Right, so we see that no matter what x and y are, whether x is bigger than y or x is less than y, this product up here is always positive. Right, so for any random variable, say x and y, we'll take f applied now to the random variable x minus f applied to the random variable y. I take the product with g of x minus g of y. So for any random variables x and y, this expectation here is going to be positive. Right, so this comes from the increasing properties of f and g. And then we can work out what this product here is. This here is the same thing as saying, what? I'll factor out, so I have f times g and I'll do this part over here too, negative f times negative g. This is going to be f of y, g of y. This is going to be bigger than, okay, so what is left? I'll have f times g with a negative sign. I'll move to the other side. I'll get the expectation of f of x, g of y, plus the expectation of, and then I'll have f of y times g of x. So now, so we have this inequality. Let's specialize further then. So this worked for any random variable. So now let me make the assumption. So assume further that x is independent of y. Right, this means that x is independent of y. Right, so remember that means that the probability that x is less than x and y is less than y, this is just the probabilities multiplied. Okay, so that's just what that means. So we take two and so now we're going to further specialize to the case when x and y are independent and they have the same distribution, that p of x less than x is equal to p of y less than x. So you have the same distribution and they're independent. Then we're going to get this quantity here is going to simplify, because if you have the same distribution, then what we're going to get on the left-hand side, whether I write x inside the expectation or write y inside the expectation, is going to be the same because they have the same distribution. And now over on the right-hand side, you see I have expectations of products. I have expectation of products, so then I can use the independence, and that says that the expectation of a product of independent is equal to the product of the two expectations. Okay, so on the left-hand side, star becomes equivalent to, on the left-hand side, I'll get 2 times the expectation of f of x, g of x. So that's going to be bigger than. And now the right-hand side, what does that become? On the right-hand side, I'll get the expectation of f times the expectation of g. And whether I write x or y is the same because you have the identical distribution. So here I can write x. And I'll do the same thing over here, and that will give me two of these. Right, so I get then that this is the same thing as saying that the expectation of f of x, g of y, g of x is bigger than e of f of x times e of g of x. We good so far? This was step one. That was the first step in the proof. If I had, so what it shows is that if I have two increasing functions, I get this property here for any random variable x. So step two is going to be to apply this previous step to prove the result, and the result is, let's just recall it, the result is this one here. So step number two, so take a function h. This is the one that we're interested in. So say that h is increasing. So take an increasing function. And I want to apply the previous result. So how are we going to do it? Well, I need f here is increasing and g here is increasing. So I need a g function. So we're going to set f of x just to be h of x, and say g of x. And g of x is going to be the one that has to do with this this one here. So here I'll take 1 minus 1 times h of 1 minus x. So this one here is increasing. And this one here we need to check. Well, if I look at the map that puts x into h of 1 minus x, well, h was increasing, so this thing here is decreasing. Excuse me. This one here is going to be decreasing. So then if I put a minus, I'm going to get that x into minus h of minus x. This is going to be increasing. So I have my two functions, and I can use step A. So by step A, from step A, we get, what do we get from A? Well, we get the inequality that says the expectation of f times g. So that's going to be h of u times, and then there's a minus sign, h of 1 minus u. This is going to dominate, and then on the right-hand side, I'm going to get f was h of u times, and then G was minus, so we're going to get another minus sign there, H of 1 minus U. Right, and now they cancel out. I'll move this minus sign to the other sign, and I'm going to get that the expectation of H of U times H of 1 minus U is less than, and then whatever I have over here. But now I'm done. This here is, when I take the difference between these two, I get exactly the covariance. So the covariance of H of U, H of 1 minus U, right? This is by definition the difference between these two. This is E of H of U times H of 1 minus U minus what's on the right hand side, H of 1 minus U. So then this is going to be negative. And that was the claim, that if I took a monotone function, maybe I shouldn't call this for G here, maybe I should call it for H, because that was what we proved it for. So let's put the H here. So then the covariance between these two, it drops, and then you get this variance reduction that we talked about last time. Any questions on this part? Could we follow? So looking at your looking at the examples that we're going to be encountering in math finance, the typical examples that one is looking at, like so in math finance, so in quant finance, you often see like H of X is either X minus K positive part, right? So that's the call option. So that's definitely going to be monotone. Or you see H of X being the put option, K minus X positive part. So that's this one, right? So they're both monotone. So this trick with reducing the variance using these antithetic variables, this works. And this here is going to come in the homeworks. Any questions or comments on antithetic variables? This was to address the question that was raised last time. It is possible to give conditions under which this covariance indeed is lower. And monotonicity, I'm sure there are other conditions one can put on, but monotonicity, this is going to cover a lot of the examples that you see in quant finance. So if there are no questions or comments on this, we'll move on to do something else. we also talked about last time, so how to generate non-uniforms. So again, the premise is that you can always generate a uniform. Just hang on a second, let's turn the heat on. This heat came up in here. Our heater in the house has this, it switches off at 8 o'clock in the morning, and I have not yet figured out how to keep it on. So it turns off automatically, and then I have to go hit the on button at 8 o'clock, otherwise it gets to be freezingly cold up here. Anyway, how to generate non-uniforms, right? So say, so we looked at this a little bit. So if x is a random variable going from omega to r, has a distribution f. So this is f of little x, which is the probability that the random variable is less than x. Then you can set u to be f, that distribution function composed with the random variable. This is uniform. And this is uniform on the interval 0 to 1. And the proof is not, we looked at it last time, the proof is not bad. It's just you take a number between 0 and 1, right? F here is a distribution function, so this is a number, right? This f here goes from R, the codomain, into that interval 0 to 1, because it's a distribution, it's a probability, so it lives between 0 and 1, right? So if I look at the proof is not bad, you just use the definition, and so the probability that u is less than u, this is going to be, we plug it in, p of f of x is less than little u. And then say that you can move f to the other side. One of you asked about how general you can do that. And so it turns out you can actually do this in complete generality, but just for the examples that we have in mind, at least today, it's f really has a genuine inverse. So say that there is an inverse function, then you'll get p of x less than f inverse of u. Right, so this will be the distribution function evaluated at f inverse of x. And this is going to, there's no x, there's only a u. This is going to give you u here on the right hand side. So you have the uniform property. And so based upon this, you can move f to the other side. So f inverse of u, so f inverse of u, this is my x. And so the algorithm is, for sampling realizations of x. Well, so first step is you sample ui, sample ui realizations of the uniform. And then the second step is you simply just set xi to be f inverse of ui. One thing that comes up quite a bit, in particular with normals, is the multi-dimensional distribution. So before we switch over to looking at some code, let me just talk a little bit about the multidimensional normal. Right, so often, not often, sometimes, this here only works for the one-dimensional case. So for multi-dimensional, but this here is normals. For multidimensional normals, there is a multidimensional normals, right? So now you have x is a vector. So x is equal to, what will we have here? x1, x2, down to say xd. So we write this where x little d is one-dimensional. So we will write at x, and this is curly one, and then you have an n. Right, and then there's going to be a mean, mu, and then there's going to be a variance-covariance matrix. Right, so in mu here, this is a d by 1. Right, so d rows, 1 column. And the variance-covariance matrix, this is a d by d. So this is a square matrix that has d rows and d columns. How do you sample from one of those? Okay, so to sample realization of x, there's an algorithm, and the first one is you start by generating a z, which is simpler. So we generate a z, which is normal, but here there'll be a 0. Right, so it'll be 0, 0. It'll be d zeros. And then the variance-covariance matrix it has 1s on the diagonal, and it has 0 outside. So these here are standard. These are, so that means is that C of the form C1, C2, down to CD has standard normals, has standard normally distributed marginals. Zi, and Ci is independent of Cj for any I that's not equal to j. Right, so the off-diagonal elements are all equal to 0. So off the diagonal, you have 0 everywhere. On a diagonal, you have 1s. There's no mean. Right, so how do you get those? Well, to get those, you say you can generate these ones. So how do you get Zi? So you set set little ci just to be, maybe it should be big ci, right? So set big ci just to be f inverse of ui, where UI is uniform, the independent UI, we need to get the independence. UI is independent of uj for any I not being j. And what is f here? F is the function that's the standard normal distribution function. So it's the integral of what is it, 1 over root 2 pi e to the minus y squared over 2 dy. So you sample the uniforms, you stick them into this inverse function, and out you get independent standard normals. So that was the first step. That's how we get the z's. So to move from the z's into the x's, and remember, x is the one that has a much more complicated structure. It has a mean and it has a variance covariance matrix. And so the second step is you're going to transform. You're going to transform this vector to get x. And how we're going to transform, this is where the tricky part comes. You're going to write sigma, the variance covariance matrix. You're going to write this here as A transpose. So this here is going to be this one here was a d by d, and these ones here are going to be d by d. And this one here, this is the transpose. So you're going to write sigma out in this product. So basically A here is like A is like a square root. But it's a matrix. So say that you can do that, then you set then you're going to set x to be the mean, right? So this here is this was a d by 1, and then you're going to take your a times z, right? So a here was a d by d, z here was a d by 1, right? So overall, this becomes a d by 1. So that's the algorithm. We're going to look at examples on the computer in a second, but the difficult part, so the first part here, there's really not much to do compared to, this is like doing the one-dimensional case. The harder part is this one here. So let me do an example on a piece of paper on this one first, and then we'll do it on the computer in a minute. So let's do an example of these this decomposition of sigma. If you look at the two-dimensional case, so then your sigma would be, you can write this here as the variances, and then outside is the covariance. So this is sigma 1, sigma 2 rho, and down here is sigma 1, sigma 2 rho. So variance is on the diagonal, and then the covariance is off the diagonal. Rho is the correlation, right? The rho is a number between -1 and 1. Rho is the correlation. how could one go about writing this? So here is one way to do it, and this is a popular one. So there's something called a Koleski. There's something called a Koleski factorization. Something called a Koleski factorization. So the Koleski factorization says you write sigma as something that looks like you have two matrices. Well, you're going to have this here is going to be your A, and this one here is going to be A transpose. And what's special about the Koleski factorization is that it's a triangular structure. So you have stuff here on a diagonal, and you'll have stuff in here. Here you'll have stuff, and then there'll be a 0 up there. And then the A transpose, well, it's going to be whatever we have here, we'll have to move it up here in the other corner. And then 0 down there. So how does the Koleski factorization look like in the two-dimensional case? Well, so the Koleski factorization in the two-dimensional case would look like, so I have my sigma. Have our sigma, we want to write sigma as this product here. And we're going to have A to be, so sigma 1, right? And A is lower triangular. So we're going to have a 0 here. And then down here we'll have rho sigma 2. And then you have root 1 minus rho squared, sigma 2. Like that's our guess for how it should look like. And then of course A transpose. A transpose, you just move this one up there and the 0 down there. So we're going to have the same thing on the diagonal. And then you're going to have a 0 on here, and you're going to have rho sigma 2 up there. And so let's just do a sanity check. If I look at A transpose, what will I get? Well, I have to multiply two matrices together. I have to multiply the top row onto the first column. That's going to be sigma 1 squared. Okay, so now I want to get the one up here. So I take the top row, and then the second column, I'll get sigma 1 rho sigma 2. Okay, then I'll go down to the second row in A. I want to get this as a value here, so that's going to be the second row times the first column is going to be rho sigma 2 times sigma 1. And then finally, to get this point down here, I'll have to take the bottom row and the second column, multiply them together. So what do I get? It'll be rho sigma 2 times rho sigma 2 plus, and then it'll be square root. That'll be 1 minus rho squared times sigma 2 squared. And that quantity here simplifies. This thing here becomes just sigma 2 squared. And that's exactly my sigma from the top. So in this two-dimensional case, I can fairly easily write down the Koleski factorization. This becomes harder in higher dimensions. So I'll show you on the computer in a minute on how one can get this to work. But now given this, then we can we can write out more specifically perhaps what this one here is. If I were to look at A Z, actually that would become the matrix I had for A, the lower triangular matrix, sigma 1, sigma 1, 0, rho, sigma 2, square root 1 minus rho squared, sigma 2. And then times Z, those are my independent standard normals. So this is Z1 and Z2. And I can work out what this is, multiply out what the matrix is. So this is sigma 1, Z1. And downstairs I'll get rho sigma 2, C1, plus root 1 minus rho squared, sigma 2, C2. And this thing here is going to be standard normally distributed. The means are going to be 0. But you're not going to be independent. Like the Z's were independent, but not when you mix them up like this. And the variance covariance matrix is going to be, when you compute what it is, it will be the variance of the first one. Okay, that will be sigma 1 squared. Then it will be the covariance between them. So that will be sigma 1 rho sigma 2. And then, of course, the same thing down here. And then the variance of the second one, well, here you'll get rho squared sigma squared. This will cancel out again, and you will end up with sigma 2 squared. So if you want to have a mean, instead of the zeros here, you will add that mean vector. And you will add that mean vector. Okay. Any questions or comments on what we just talked about in terms of Cholesky factorization and getting the square root matrix A? No, I want to look at a little example. Let me switch over to my screen. So again, I'm going to use MATLAB because this is good enough for illustration and here in class. And the file I'm looking for is and it's this one here. Okay, so what we're looking for, take a matrix. So can you guys see my screen? Just double checking. Can you guys see my screen? Yep, we can see the screen. That's good. So this is how the code looks like in MATLAB. So start out with a correlation parameter. So say that rho is equal to, I don't know, 0.5. And my matrix that I seek to factor out, this is my sigma. So let me just turn all these ones here off. So I do a Cholesky factorization. So let's see how the Cholesky factorization looks like when rho is a half. I want to see the matrix. So that's the matrix. Just one thing to note here, and this might be true in other cases too. When I call the Cholesky factorization in MATLAB, it gives me an upper triangular matrix. So if I don't put the transpose there, you'll see that it switches the half from being down in the lower left corner to being up in the upper right corner. But the theory that I just did on paper, it requires a lower triangular matrix. And the way you transpose in MATLAB is by putting this dot up there. It's not a T. Okay, so then what we want to do is we want to use the algorithm that we had. And the way we do that is generate the uniforms first. So the ones that I've stored in Z, maybe I should call them U, to follow up with what we had on the slide. So you take uniforms. So I want however many samples of them. If I want 10 samples, I want these uniforms, and I'll store them in a matrix that I call little u. So here, this will give me a matrix. So it'll have there'll be 2 rows and 10 samples. So we'd be simulating 10 pairs of uniforms. And so then the first step is to transform them into standard normals. And so looking at the slides from before, we need this inverse function. We need this inverse function of the standard normal distribution. And in MATLAB, that function is called norm INV. So if we want, we can look up you can look up the function in MATLAB. So norm ENV, this returns the inverse. It returns the inverse of the standard normal distribution. And of course, if you want to have different mu's and different sigmas, you can do that. Okay, so norm ENV, this is the command in MATLAB. You need to figure out what it is in the package in C++ that you're using. So by calling that, I'll plug all the uniforms that we just sampled, and I'll plug them into this matrix C and see how that looks like. So inside U is where I have the uniforms. Inside little z, this is where I'll have the standard norms. And you can see the uniforms when I run it in MATLAB. I get these numbers between 0 and 1, but of course, when I transform them into uniform samples, I'm going to get numbers that are between -∞ and +∞, clustered around 0. Okay, so now I'm ready to do. I'm ready to simulate these uniforms here in that little in the matrix that's denoted by little c. These are independent. Right? These are independent normals. And so to make it work, I need to multiply them onto that Koleski factorization that we have stored inside A. Okay, so I will do that. And that's over in my code. Those are my x's. We just call them little x. And so here's what we see the code. You get the x's. You get the x's from taking the Koleski factorization, multiply them onto the independent normals. And this is going to give me now the dependent normals. So if you plot both z and x next to each other, we can see the difference. So upstairs in my z, this is where upstairs in my z, this is where I have the independent normals. And down here with the x's, this is where I have the dependent normals with the correct correlation structure. And of course, we can have a look at how they look like. If I scatter plot my x's, This is a scatter plot of the axis. There will be some correlation between them. And if I increase the number, maybe it's more, you will see the pattern more clearly if I move up to say 100. Still plotting something. Now we see the picture. There is some dependence between them, and of course, if I increase the dependent structure to be say 0.9, I'm going to see positive correlation. So they are centered around 0 and they are positively correlated. And of course, there are some outliers. Any questions on this? One thing that we're going to be doing a little bit later is talk about, some of you might have noticed that this is called copula. It's called Lec2A copula. And we haven't talked about copulas at all at this point. But so let me just preempt a little bit about this copula structure. If I go back and instead of scatter plotting the normals, if I just scatter plotter the uniforms, so now I'm going to get independent uniforms. So I'm just going to get something in the unit square, and it's just all over the place. Right? These are the uniforms. That are independent. But you see, I have Gaussians that are dependent. Those are my x's over here. After I did this trick, I get Gaussians. I could now transform the Gaussians. I could transform the Gaussians. So this here's my copula. This is U dependent. Like the ones we looked at here, those were the U's that were independent, but I could transform back. I could transform back all the correlated normals back to uniforms by plugging them into the normal cumulative distribution function. So this is going to give me uniforms now, but they are going to be dependent. So if I scatter plot this one, so let me just get the code right. So instead of plotting the independent ones, I'm going to be plotting these dependent ones. So now we're going to get dependent uniforms. And you can see this. These are uniformly distributed, but they are dependent. There is this positive correlation structure in them. And of course, if I go up here and change the correlation to be like minus, say, 0.4, then we're going to get them sitting on. It's not going to go in the positive direction. It's going to be in a different direction. So this idea that you can take you can start out with uniforms, then you can move them into the correlated Gaussian case, and then you can transform them back into uniforms. This has to do with copulas. So a copula is a multidimensional distribution that has marginals as their uniforms. So when you're looking at a picture like this one, when I'm looking at the marginal distributions, there are two of them, right? There's this is a two-dimensional setting. So the marginals are uniform, but they're not independent. And you can see that if maybe visually, if I increase it increase the correlation to be something much bigger, you can see that looked at marginally, you're going to have uniformity, but looking at them across the two-dimensional, there's definitely a pattern that emerges, and it's this negative correlation. But this here is at the uniform level. This is not, I could plot this one here too, as we looked at before, at the Gaussian level as well. But to get copulars, you have to have uniformity of the marginals, but potentially a complicated correlation structure like the one we're having here. So for those of you that are interested in credit risk, often there's a student or two that are interested in credit risk. If you're interested in credit risk, working with copulars, this is a key. These models that people used and continue to use related to credit risk, there's always a normal copular model in there. Are there any questions or comments? Are there any questions or comments about what we looked at here? So when I was prepping this lecture, we got down to this decomposition, this factorization of the volatility matrix into this Koleski factorization, and then you wonder, like, okay, so this is one way to do it. There could potentially be many other ways to do this square root, and that's the case. There is, and so let me show you another way to do it. And so when I was doing this, I remembered that a number of years ago, there was a discussion that came up in one of our seminars, and I asked the presenter about something called principal component analysis, and the speaker didn't know what that was. And so this kind of stuck with me because I thought this was something that when you took classes in linear algebra, that you would be taught principal component analysis. And I naively, I thought that was the case. And it turns out that that's not the case at all. So I don't know, for those of you that are taking courses in linear algebra, have you seen principal component analysis? It's called PCA. Has anybody seen PCA? It's okay if you don't have it. It's taught in econometrics. Okay, so it's not taught in linear algebra, right? So I think this is something that people should see. and it's related to what we've just been doing. So I'm going to spend like an hour going over principal component analysis, and we're going to do an example with a principal component example with numbers in MATLAB, so you guys can see it. It's like it's just a very nice application of linear algebra, right? I bet you most of you have tried to use PCA even though you had no idea that this is what was going on. Like, everybody has tried to zip a file. Everybody has tried to compress data. And if you ever wondered about, like, how does my computer compress data? I bet you there's a principal component analysis that is inside that data compressor that you're using. It might not be exactly what we're going to be doing, but this idea to use principal component analysis to compress data is just a wonderful application of linear algebra. And it touches upon eigenvectors and eigenvalues. To me, I think this is something that we ought to know, and it has to do with data, and it's closely related to this Koleski factorization that we just did. So let me show you just a little bit about principal component analysis. This is not like going to be a huge thing, but I don't mind spending like an hour talking about this. So if you have seen it before, go get a cup of coffee. If you know how to do it, if you already have worked with it, just take a little break. For those of you that have not seen principal component analysis, here's a chance to get like some feeling of what principal component analysis is all about. So we're going to do a little detour. So a little detour. So it's called principal component analysis. So PCA. What we were looking at was we were interested in decomposing sigma as A transpose. There are many ways to do this. So there are other ways, maybe we should say alternatives. There are alternatives to Koleski. Koleski is the one that everybody favors because it has this triangular structure, so it's very easy to work with. So there are alternatives to Koleski. And so here's one. Like this sigma, our sigma is symmetric. And it's positive semi-definite. Spell definite. So what that means for us is that sigma has D positive eigenvalues. And we can write and I'm sure some of you have seen this in linear algebra, that you can write your sigma in terms of these eigenvalues and eigenvectors. So you can write this here as a V, and then a D, and then a V transpose. Where the D here, this is diagonal, that's why it's called a D. D is diagonal, so this is a, these eigenvalues are denoted by lambda1, lambda2, up to lambda D. So on the diagonal of D is where you find these eigenvalues. So this is lambda1, 0, 0, 0, and then 0, lambda2, zeros. So that's what D is. And then over here is where you find the eigenvectors. V is, I mean, this is is a D by D matrix. This one here is a D by D matrix. V is equal to eigenvector 1 up to eigenvector D. These eigenvectors, they are orthogonal. Right, the orthogonal. And you have norm 1. So the norm of V, which is just VI transpose V. This is equal to 1. Actually, the orthonormal, orthonormal. So that just means that the perpendicular, the orthogonal and of length 1. this is exactly what we're used to in the standard basis, right? The standard basis, the standard RD basis is like it's 1, 0, and then it's 0, 1, and then zeros everywhere. Right, that's the standard RD basis. All these are orthogonal, right? When I take the inner product between this guy and that guy, I'm going to get a 0, right? I'm going to get 1 times 0, 0 times 1, and 0 times 0, and so forth. And I add them up. I'm going to get exactly 0. If I look at the length of it, well, it's 0 squared, that's a 0, 1 squared, that's a 1, 0 squared, that is 0, and so on. So this is going to give me exactly that the length is equal to 1. That's the standard RD basis. So now we're going to have a new one. So there's going to be a new basis of the new basis is going to be these. If I look at the span, these eigenvectors up here, B1, B2, up to BD, I'm going to get RD. This is a new basis for RD. These span everything. I have D independent vectors. All right, so if you go back to what we had before, if I have these decomposition, from before, right? So it's one alternative to Koleski we need to write, right? Our goal was to write sigma as A times A transpose, and so we have now sigma written as VDVT. And so we just need to take a square root of D, but that's easy because this is a diagonal matrix that has non-negative numbers on the diagonal. So we can write here A to B, if we want to V. That's the matrix of these eigenvectors, and then we multiply them onto, and we need a square root here. So we're going to put square roots on the diagonal and just zeros outside. So here I'll have a square root of lambda1, square root of lambda2, square root of lambda d, and then zeros out here. So that's an alternative to Koleski factorization. So when I got down to here, so we could stop here, or we could spend a little bit of time to talk about principal component analysis. So here's an alternative to Koleski, but one can actually, it is hard to, it is by itself, doing what we have here is subpar compared to Koleski, because Koleski has a triangular structure. Like this thing here is not going to be a triangular structure. Like V here consists of all these eigenvectors, right? And there's not going to be any triangular structure here. So this one here is subpar to Koleski. One would not use this approach to do to simulate correlated multidimensional normals because you don't have any advantage to doing that over Koleski. So why go through all this? Well, I want to show you how one can apply this to principal component analysis. And today, so we're now going to let go a little bit of simulation, and we're going to move into principal component analysis. So let's try to do PCA. So you're given data. You're given data points. And let me call them xn. The xn, how many of them do we have? How many of them do we have? n. We're given data points, and xn is a vector in D. So now the idea would be to compress data to compress. So this is also the same thing as project data to R, say M, where M is much smaller than D. So just maybe just to illustrate, if you take, I can draw in 2 dimensions. So if I draw, if I take D to be 2, and then, well, there's not much left, right? I'm going to take M to be 1. So what we do is we have these points and these scattered around in here. So how would we do this? These are my xn's that are floating around in here, and what one could try to do is, if you want to project it into a space of a smaller size, project it into a one-dimensional space. So instead of having a plane, we project it onto a line. So we'll try to find a line in here. This is my smaller space. And where do we want to put the line? Well, one thing we could try to do is we could try to compute the distance. We could try to compute the distance to all these points and then minimize, and then put a straight line in there. Okay, so find the linear subspace. Like, remember linear, this is what it means when it goes through 0 here. Find a linear subspace that's closest to all points. And this here will be my, this object here, this will be exactly my, this will be my eigen, this will be an eigenvector. This thing here is given by 2 coordinates, right? I go 1 out here, and then I go something up here. So this is going to be, if this is my V, so this thing here, this is characterized by a vector V. So it'll be a 2-dimensional object, V1, V2, right? And the length of it is 1. Here I'll go V1 up there, I'll go V2 up there. That's my linear subspace. I'm not worrying about the intersection. Just for what I'm going to be presenting here, I'm not going to be worrying about the intersection. You can also move it up and down here. I'm not going to do that. Just keep it simple. But so this is what happens in 2 dimensions. Try to find this subspace here that is the closest to all these points. And right, there are lots of them. Compute these distances, you add them up and try to minimize, and this is going to be a space. Okay, so how do we do the general case? So the general case, you say you'll have these vectors, I'll call them for B, B1, B2, up to BD. And these are an orthonormal, normal basis for RD. So because it's an orthonormal basis, right? So you have length 1 and you're all orthogonal. I can write my data. I can write my data as, what will I do? I would say, I will be summing. So I will be summing, maybe I should call this for D. I'll be summing these up. So it'll be a linear combination. I can express each data point as a linear combination. And then I have to multiply on the constants here. So I'll call these for beta, D, and then N. These ones here are constants. Beta, D, N. This is just a constant. This is the loading. Loading on the dth basis element. Loading on B, D. So there's nothing mysterious about this. Again, as an example, if I'm looking at a two-dimensional object, the standard basis. So if I were to write the element 7 and 3, I would write this here as, what would I write it as? I would write this as 7. So this here would be my B1 and B2. So I'll write this as 7 times 1, 0 plus 3 times 0, 1, right? So this here will be my, this will be my beta, beta. This here is my xn. Then this will be my beta 1n. This one here would be my B1. This one here would be my beta 2n. This one here would be my B2. So I can express my data, instead of expressing it in the usual basis, I can now, if I have such an orthonormal basis, I can express it in terms of that basis. And so the coefficients, so if I have this representation, what will my coefficients be computed as? How do I get my hands on these coefficients? So again, keep in mind this x here, this x here, this is a vector in RD. So this is a 1 by, this is a D by 1. Right, there are D rows, 1 column. This one here, this is the orthonormal basis. So this is the basis vector. This is a D by 1. This one here is a 1 by 1. This is just a coefficient, and this is a vector. How would I get my hands on the coefficients? So the loadings, these are these beta DNs. They are found, what are they found as? If I look at xn, so xn, this is a d by 1. So if I transpose it, I'm going to get a 1 by d. And then together with bd, what would I get? This one here, this is a d by 1. So this here is overall 1 by 1. And that's going to be my beta, hopefully. So let's work out what it is. But this is going to be the inner product. This is the inner product between xn and b d. So we plug in what xn is. This is the sum from d equals 1 to, so maybe I shouldn't use d here. Let's use k going from 1 to d of beta kn bk together with bd. Right, so it's an inner product. And what do we do? An inner product is linear in both entries, so I can pull the sum outside. I can pull the sum outside. And I can pull the coefficients. Pull those outside. And then I have the inner product between bk and bd. Well, I know exactly what this here is. They are orthonormal. So that means that these things here will be equal to 0, except when k is equal to d, and they'll be equal to 1 exactly when k is equal to d. So overall, this here becomes beta dn. Right, so another way to express these coefficients is exactly as what we have up there. We good so far? Okay, so how do we compress data? Well, we have this formula. We have this formula for my data. I can write it in terms of these. I can write it in terms of these basis elements. Right? So I can write here xn. I can write this here as, if I break it up just into two sums. So d equals 1 to say m. Like I want to get it onto a smaller space. So let me sum up to m here of my loadings times the vector. And then of course the remaining part. There should be a d here. So what I want to do is I want to compress it. And so my compressed data is going to be denoted by xn star. And I'm going to approximate these data points up here by the first component here. So if I want to get it onto the m dimensional subspace, I will just take out the first part here. And then if I look at the difference, xn minus xn star, but this here is still going to be an element. This is still an element in RD. This part here, after all, this is a basis vector for RD, so this will be a d times 1 element. So this is still an element in RD. And if I look at the difference between these two, then what I'm left with is the second term up here. So I'll write out that second term. And if you want, we can plug in the formula we derived on the previous slide. We're going to need that in a little bit. The formula that we derived was that BD could be written as this thing up here. So instead of BD, beta dn, I'll write X transpose B. So this here is X in transpose. This is the inner product between xn and this d basis element. times BD. And what I'm interested in is, I'm interested in making this thing small. I want to choose these basis elements to make this difference here small. Okay, so let me look at the difference. So the norm, say squared, what is it going to be? Well, it'll be that mess we have here. It'll be that mess we have here times BD squared. And so here comes the time where we're gonna use that we have basis elements here. So the orthogonal. So I have the norm, and these are orthogonal. So I can factor it out simply by moving the sum outside. These were coefficients, so you're going to get squared. And then we're going to get the norm of BD squared. Well, we know what that is. That is equal to 1. So we end up with this objective. We end up with this objective, which is d equals m plus 1 to d of x and t b d squared. And what does that have to do with the comments in the beginning about these orthogonal and eigenvalues, or the eigenvalues and the eigenvectors that we were talking about before? Well, it's going to have a lot to do with it, because I can write this last term here, this square. I can factor out this square here. I can write this out as a sum from m plus 1 to d. And what I can write here is BD transpose. And then I can write xn, like there's a square out there, and I can factor it out. And then I'll have xn transpose BD. And let's just do a sanity check. Make sure we get the dimensions correct. So xn here, this was a d by 1. xnt would be a 1 by d. BD would be a d by 1. And if you transpose that, you're going to get a 1 by d. Okay, so it looks like it all works out. Like in the end, this is going to be a 1 by 1, and this is going to be a 1 by 1. Okay, so it's going to give me that coefficient up there. So here's where the eigenvalues come in. Define the covariance matrix. Define the covariance matrix S. I'll have 1 over, remember the discussion we had last time? Either we do 1 over n, or we do 1 over n minus 1. In practice, when n is very large, it doesn't matter so much. When n is smaller, it matters more. But let me follow what we did last time and divide by 1 over n minus 1. And then we'll be summing. And this is where I'm using that the mean of these xn's. I've subtracted it away. Otherwise, you need to do a correction here. But let me just forget about the means for now. I'll do xn, xnt. That's the quantity that appeared up here. And this one here, this is going to be a D by D. This is a D by D matrix. It's the covariance matrix. So now our goal is to try to minimize. Our goal is to try to minimize what we have here. So I want to plug that in there. So minimize the sum from D equals M plus 1 to D, and then you have your BD transpose, and then you have your S, and then you have your BD. Minimize this expression here over BD plus 1 all the way up to BM, such that what? Such that Bj is orthogonal to Bi, and the length of them always equal to 1. And how would one go about doing that? Well, this is where that matrix thing with the eigenvalues and the eigenvectors come up. If I form this is a maximization problem, is quadratic, and this is a maximization problem with a side condition. So to do that properly, you need the Lagrangian. If you haven't seen optimization problems with the side condition, then you have to believe me that you need to form the Lagrangian. The Lagrangian, so we call it L. It's the objective to D of what we had up here, BD transpose S BD. But now there's going to be the side condition. The side condition is that you're only maximizing over vectors that have length 1, and you have to be orthogonal. So you're going to subtract away, maybe you're going to add depending on the sign of the Lagrange multiplier. So here you will have a D you'll have side condition. So this will be the Lagrange multiplier, lambda D, and there'll be 1 minus, and then the norm, we can write the norm as BD transpose BD. Right, this quantity here, this is the Lagrange multiplier. And then you maximize this, and this is unconstrained. But it's a higher dimensional one because there's a Lagrange multiplier that you have to determine. And what we do is we take the derivative with respect to one of these quantities we want to maximize over. So let's take a BI. We want to plot that equal to 0. It's a quadratic problem, so taking the derivatives will give us something that is linear. What we'll get here is, I need to take the derivative with respect to, say, BI, and then I can combine these here. I'll get the derivative of BI T, and then I'll have S BI, and then I'll have my lambda, that's a constant, lambda D, and then B, not D, lambda I, BI. So I compute the derivative here, plug it equal to 0. That's going to tell me that S bi got to be equal to lambda bi. And that's the magic part. This shows that bi, so bi is an eigenvector. For the variance covariance matrix, and lambda is an eigenvalue. So if I want to make the approximation error small, I need to have these remaining. You have to have these remaining vectors to have large eigenvalues. So that's the key thing. So so you need to choose these b. What you were started at m plus 1. M plus 1, M plus 2, all the way up to the last one, with the smallest eigenvalues. So your factors, this will be your B1 up to Bm should have large eigenvalues. Have the largest eigenvalues. This is how you do data compression. You need to compute these eigenvalues, you order them, and you see how big they are, and then you pick the ones that have the largest ones, and that's going to be your factor. So this might seem very abstract, and it's not really that bad when you look at a specific example. So I had a specific example in mind. Let me just pull that up on the screen, and then hopefully it might seem abstract here on a piece of paper, but it is really not terribly hard to perform in on a computer. So let me just show you how to do this. Let's see. So that was the other one, PCA. Okay. There's a lot of notation. Let me just factor it out so we can get started. I was playing with it yesterday, prepping the lecture, and I got it to work in the end, so I'm hoping that it's going to continue to work today. Okay, so there's a data set here. I'm going to work on something called ingredients inside the data set. I don't even really know what it is. It's just a data set. And let me show you how it looks like when we get it up. This here is the data set. So it's not terribly complicated. If I calculate I think this should be what we call this one in. Yeah. So if I calculate the dimensions of it, I have I'm living in a 4-dimensional space, and I have 13 observations. So in that in this matrix, each observation is a row in the matrix called ingredients, and I have 13 rows. So I'm living in a 4-dimensional space, and I seek to compress data. So then we need this covariance matrix. And this is this S matrix here. It's very easy to call. In MATLAB, you just call covariance and it will give you what this is. And as usual, the thing to note is, what does this covariance command actually do? And if you go over to MATLAB and you search for the command, you go in here and it'll return the covariance. Okay, so then the thing to look out for is this n or n minus 1, which we talked about last time. We also mentioned it today. And here it says, C is normalized by the number of observations minus 1. Right, so that was what we had too. We divided by not n, but n minus 1. And so this is the standard that it does here. If you don't like it, there's probably a way to undo that. So I'm happy doing that. So the covariance matrix that it computes is already normalized the way that we want it. Okay, so now I have my covariance matrix. I don't need to keep plotting. I should also say here, what this command here does is that it normalizes the data that I have such that it's centered around zero mean data. So I'm just subtracting away the mean. I'm just subtracting away the mean, so I don't have to worry about this affine push. We talked about, we're looking at linear subspaces. If I don't do this normalization here, I have to worry about the intercept, and I don't want to do that. So I'm just centering my data such that it has zero mean. This is all it does here. I take the data and I just center it around 0, so just subtract off the mean, and then I compute the covariance. Okay, so the next line of business is to calculate the matrices of eigenvectors and the matrix of eigenvalues. And this is what I'm doing here, V, and then this diagonal. And again, it's fairly straightforward to do in a coding setting like this one. There'll be 4 vectors and there'll be 4 eigenvalues. And so these store over here. And because the covariance matrix S is positive semi-definite, we know that these eigenvectors, these eigenvalues are going to be positive. And you can see that's the matrix D that has these eigenvalues on the diagonal. And in this set here, you can see that they really vary in size. Right? The smallest one is a lot smaller than the biggest one, right? The biggest one is 517, the smallest one is 237. And up here in these columns, this is where you find the eigen vector corresponding to this eigen value is what you find in the first column in V, and so on. And so based upon the discussion that we've had, like you have these 4 columns in V, they will give you a basis, the orthogonal. You can see that if I call, say, V of, if I call the first one, right, that's the first one I have. And then if I multiply it, if I compute the norm with, say, the second one, I should get 0. That's what I get, very small number. But this here is the inner product. And likewise, if I compute the norm of itself, I should get a 1, which is what I get. So it consists of these basis elements. There are 4 independent vectors. It's going to give me a basis. Which one should I use? Well, there's one that sticks out quite a bit, right? This is a much, much bigger eigen value than all the other ones. So I'm just organizing them over here primitively. E1 is the biggest eigen. This is the biggest eigen value, and so on. And the B's, those are my corresponding eigen vectors, and B1 is the one that has the biggest one. Okay, so I got my data and I got it organized in these vectors. So maybe we should just do a sanity check, make sure that it runs the way that I want to. So if I call B1 here, this would give me the biggest one. This would be the last column over in V. And it does. And if I call E1, I should get the biggest eigenvalue. And I do. So the idea would be to see, I have my general data inside ingredients. If I print out the ingredients, we'll be able to see it. Print out the ingredients. So this is a 4-dimensional object. So the one proposal is to, instead of having this data expressed in terms of 4 basis vectors, I could express it in terms, I could compress it and express it in terms of the last one, the last 2, the last 3, and of course I could express it in terms of all 4, in which case there'll be no difference between keeping all the data or expressing it in terms of the 4 bases. Okay, so let me try to look at these various things. Here I'll have I have 4 options. I will do the betas. This was the loadings, the coefficients. So there, those are the ones we calculated, where you take the ingredients, that was my x, times these basis vectors. And then you can start approximating. Here there are, those are the ones that, like what kind of, what do we get out if the first one is when I, use the entire, I use all the basis elements. The second one is when I use, the first one is when I, the one I'm interested in is number 2. This is when the first basis element is what I'm using to approximate, and then what we get in getting here is the error that remains, and so on. And we can calculate this. We can calculate these errors that we're making. I calculate them in 2 different ways using the eigenvectors, right? So the first one is going to give me the overall error, and then we can see how the overall error it changes as I let go, as I include or exclude more and more basis elements. So we try to run it. Oh, and this was M. This should have been N. Ah, 51 should be N. So if I'm not to get the if I'm looking at the last one, that's the number 4, that's the E4. If I'm looking at that one, this is when I'm approximating using the first 3 elements as my, I'm using beta 1, beta 2, and beta 3 to compress my data. So I'm compressing it onto a 3-dimensional space. Okay, so then the error that remains is fairly small, right? The only thing that remains is the error coming from the eigenvector with the lowest eigenvalue. The second one up, this is the second one up, this is this 12. And the second one up, this is going to be where where I'm using 2 eigenvectors to approximate. So my lower dimensional space is 2-dimensional. So I'm projecting from a 4-dimensional space to a 2-dimensional space. And this is the remaining error. This is this quantity that we have over here. This is the remaining error. And that will just be the sum of the lowest two eigenvalues, because those are the ones that I'm excluding. And so on. So the overall error is the sum of all the eigenvalues, and so by just that's the overall error that I have, and by projecting onto the subspace, the one-dimensional subspace with the highest eigenvalue, you can see the drop goes from 597 down to 80. 80 being the sum of the lowest three. So just by picking this eigen vector with the largest eigenvalue, I can dramatically reduce the error. Right? It goes down by 517.8. So 517.8, so 517 divided by the overall error, which was 500 and, what was it, 98. This is like the first vector explains 86%. Right? So by compressing from a four-dimensional space down to a one-dimensional space, I can explain 86%. So then, are you willing to live with the remaining 13% to get a data compression from a fourth-dimensional space down to a one-dimensional space? Well, that will then be up to you if you can include more and more. Yeah. This was a little bit about principal component analysis. Are there any questions? Any questions on principal component analysis? So I wanted to show you this guy. I wanted to show you guys this material because it was related to this Koleski factorization that we had done, and it's another way to create the square root matrix. But when you look at it, it doesn't seem like it has any good features, and that's misleading because it really does have properties that the Koleski factorization does not have. Indeed, it can be used for this data compression, this principal component analysis. If you have a high-dimensional space, in this example we looked at, it was a four-dimensional space where we had a bunch of points, 13 points in a four-dimensional space, and that's just typically way too much. And so you just, in this four-dimensional space, there will be a basis consisting of these eigen vectors for the covariance matrix, and you can ask, if I just include 3, if I include 2, if I include 1 of these basis elements, if I just write my data in terms of, right, the data can of course be expressed perfectly in terms of all 4, but what happens if I throw away those terms that are related to the basis elements with the lowest eigenvalues? How much does it matter? And as you can see in this simple example, it can really be that it doesn't matter very much. And then you can get away, for example, by projecting from this fourth-dimensional space down just to a one-dimensional space, you can explain upwards of 86% of all the data. And you might be willing to do that. You can look at, I was trying to look around for examples, maybe pertaining to quant finance. And there's always, for those of you that don't have it, maybe you want to consider getting your hands on this book here, John Hall. This is definitely a classic in quantitative finance. I have a 6th edition. I don't know what edition he's up at now, but this one here is this is a bit old. Let's see how old it is. See how old. This edition here is from 2006, and you can see they're coming out at a steady pace every few years. So we're like, so how many more editions has he spit out since 2006? There's one in 9, 12, so maybe 4 or 5 editions later. So you can go all the way up to edition maybe 11 or 12. I guarantee you it's the same thing in every single book. There's no need to go all the way up there. You can see this is from back in the days when you're still given Windows 2000, Windows XP, and all that good stuff on a CD. But what I was doing prepping this class was I said, well, let's see what he says about principal component analysis. And he has something on page 450. Okay, so let's go have a look at page 450, what he talks about. Well, what he talks about is a data. Here's his matrix covariance, the variance covariance matrix that he has. He has 10 factors. And 10 factors, he's looking at bonds of various maturities, and he's trying to explain something using that. But you see, he goes all the way up to 10 factors. In general, this is, I was a little bit surprised when I saw that the standard is to use 3 factors. This is how far up you go. And that was also explained on, you could see it in the data that we had here. The lowest eigenvalue in that data I showed you was like 0.23. Right, so if I did 3 factors in that model, I would have 99.3% explained. He goes all the way up to 10, and I think this is perhaps a bit overkill, but it will give you an idea about what kind of principal component analysis that he would care about in 2006, and this was to explain variations in zero coupon bonds, or in yields. These are these rates that he's talking about of various maturities. And down here, if you look at the bottom of the page, you can see the ranking. Like it tapers off. So this is what would amount to our highest eigenvalue, and then it would taper off. He has normalized them slightly differently, but I don't think that the point being exactly the same. This is your eigen, this is your highest eigenvalue, this is the most important principal component, and then it tapers off. Yeah, are there any questions on principal component analysis or what we've been doing in the first part of the lecture? If not, I say we take a break and get back together in like 10 minutes or so. Remember to change over to a different Zoom link, and then we'll continue with the remaining part of this lecture. Okay, see you guys in a little bit.